Hello everyone, in this video we're going to be looking at an A-level differentiation question. So let's have a look at this one. So it's a good, nice exam question we've got here. So it says, show that the x-coordinate of the turning points of the curve with the equation y equals f of x satisfy the equation tan x is equal to 4. Okay, so first of all, we're going to need to differentiate our equation. So let's write down our equation, what we've got here. Okay. So we're going to be using, the first thing to note is that we're going to be using the product rule in order to differentiate this. Okay. So we can think of that as our u and we can think of that as our v. So our f dashed of x is going to be u dash v add u v dashed. Okay. So let's first of all think about differentiating these various aspects. So over here, we can make a note that our u is our 10 e to the minus 0.25x. So therefore, our u dashed is going to be 10 times by minus 0.25 e to the minus 0.25x. Because when we're differentiating an exponential, we basically times by the derivative of the power. Okay, so the derivative of the minus 0.25x is minus 0.25. So we're going to do that there. So our u dashed is therefore 10 times minus 0.25, which is going to be minus 2.5 e to the minus 0.25x. Our v is sine x. So therefore our v dashed sine differentiates into cos. So we've got all of the elements that we need to sub into the product rule now. Okay, so now let's sub in, see what we get. So our u dashed is our minus 2.5 e to the minus 0.25x times by our v, which is sine x. Then we're going to add our u, which is our 10 e to the minus 0.25x times by v dashed, which is cos x. Okay, now that is all of the various elements subbed in. So into the product rule. Now, because of the fact that we're told that we're trying to find the equation of the turning points, you'll notice the question says the turning points. So therefore, what we need to do is we need to set this equal to 0. So because it's the equation of the turning points, and the turning points are where f dashed of x equals 0, that is going to be the equation of our turning points. So now that we've got the equation of the turning points, what we can do now is, having set this equal to 0, you'll notice we have a common factor of e to the minus 0.25. So in this particular instance, we can divide all parts of the equation by e to the minus 0.25 and basically simplify that. So we end up with 0 is equal to minus 2.5 times by sine x plus 10 cos x. So we just divided all through by e to the minus 0.25, and now we can just rearrange this equation. So let's add this over to the other side. So we have 2.5 sine x is equal to 10 cos x. We're aiming for tan x is equal to 4. So I'm now going to divide both sides by cos and divide both sides by 2.5 as well. So I'm going to have now sine x over cos x is equal to 10 divided by 2.5, and that gives us that tan x is equal to 4 as required. Okay, so that's our 4 marks for part A done. That was quite nice. Now, it says figure 3 shows the sketch of part of the curve with the equation y is equal to f of x. Sketch the graph of h against x, where h of t is equal to the modulus of the original question. So what we've got is we've got a graph, which is, you can see that the function is essentially the same as f of x, but h of t, the difference is it's the modulus of f of x, rather. Okay, so let's have a look at tripping over my words there. So let's have a think about this. So here is our f of x, okay, going like this. And there it is. And if we want the modulus of that, what's going to happen is all of these negative bits are going to be made to go positive. Okay, so we're going to end up with some kind of like Loch Ness monster kind of like looking type thing like this. Okay, so this is our graph of h of t. So that bit's gone up there, that bit's gone up there, and that bit's gone up there. And so that is what our h of t is going to look like. So that's gone up there, and that's gone up there, and that's gone up there. Perfect, showing the long-term behavior of this curve. Yeah, that's more than sufficient to get our 2 marks there. Now, the next bit, it says, using this model, find the maximum height of the ball between the first and second bounce. Well, let's have a look at the question. So it says, the function h of t is used to model the height in meters of a ball above the ground t seconds after it's been kicked. So you've got to be a little bit careful here because we need to think about which part we're looking for. So this is where the ball is first kicked in the air, so it hasn't bounced at all. This is bounce 1, and it goes up, comes down. This is bounce 2, okay? And so we're being asked to find the maximum height of the ball in between the first and second bounce. So in other words, we need to know what is this value here. So we need to know what's the value of t at which that occurs. Well, we found out in part A that the equation controlling all of these, the equation governing all of these turning points is the fact that tan x equals 4. So tan x equals 4 is the equation. The solutions to tan x equals 4 are giving us all of these points here. So if we say x is equal to inverse tan of 4, then that is going to give us the first point here. So we're just going to do that now. So we get our calculator and we do inverse tan of 4, making sure that we're in radians, okay, because we are differentiating trig functions. And you can see that we get the first solution is 1.325, okay? So x is equal to 1.3, or rather t, and it says 3258. And then the next solution, we're going to be adding pi. So 1.3258 plus pi is going to give us the second solution, the one that we want. Okay, so when we now add pi to that, that gives us that our x is equal to 4.467. So that's the value of t for where the second maximum occurs. Okay, so what this means for us is we need to work out h of 4.467, and that's going to give us the value of the maximum height. Okay, so let's sub that into the equation. So that's going to give us the modulus of 10 times by e to the minus 0.25 times by 4.47 if I round it up, times by sine of 4.47 as well. Okay, so we evaluate that, and our h of 4.47, when we put that into the calculator and work that out, that gives us a value of 3.18 meters, 3.18 meters to 3 significant figures. Okay, so that's our value there that we need for that one. Good, that's part C done. Okay, great. Now the last little bit, let's see what we need for the last bit. The last bit, it says, explain why this model, explain why this model should not be used to predict the time of each bounce. There is something very subtly wrong with this model, okay? And the thing that's wrong with this particular model compared to real life is that although I haven't perhaps represented it all that well, these distances in our model are all the same, okay? So these distances are the same. Whereas in real life, when a ball is kicked up in the air and it bounces, what happens is it bounces, it bounces, it bounces, but you'll notice that the time in between each bounce is reducing. And our model that we've got does not reflect that. Okay, so for part D, we would say that in a real world situation, the time between each bounce should reduce. However, the model that we currently have does not reflect that. And that's the end of how you do that question. I hope that you found that helpful, and I will see you in the next video.